All right, so let's finish up discussing integrating non-negative functions by proving some deep results on interchanging limits and integrals. So before I prove anything, I want to make something clear. Let's say we have Fn measurable, non-negative, and Fn converges at pointwise on E. So we know F is measurable and obviously non-negative, so the Lebesgue integral of F has meaning. It could be infinity, but it still exists. Regardless, there's just no reason at all to think that the limit of the integral, which is the integral of f of x, sorry, the integral of the limit, which is the integral of f of x, should be the limit of the integral. Okay? And let's just see why this is not necessarily true with two very simple examples. Okay, so the first example, let's say Fn of x. Sorry, give me 1 second. So in this example, let's say Fn of x is n times the characteristic function of 0 to 1 over n of x. And actually, I want the half open, half closed interval, not the closed interval. So let's make this half open, half closed. Okay. So yeah, the picture is just as follows. Kind of the obvious picture here. Here's the y-axis, the x-axis. So let's say here is 1 over n. Let's say here, let me make this a little better. Not that it matters all that much, but anyway. Okay, so let's say here is n. So it's going to be the step function here. Okay. And actually at 0, the value is 0. So yeah, so it has this jump here at 0. Okay, so it's pretty trivial. And I should mention here that let's say E is 0 to 1. Okay. Right, so this integral here for each n is obviously just 1. We're just integrating the step function here. So it's just this area under the curve. So it's 1 over n times n is 1. Okay. And you can check very easily. Leave this for homework. Don't know if I'll collect it or not, but point-wise, this equals 0 on 0 to 1. I mean, there's really nothing to prove. I should say there's nothing to prove. Basically, when x equals 0, Fn of x is 0, so the limit is 0. When x is not 0, well, all you do is pick n large enough so that 1 over n is smaller than x, so Fn of x is 0 for large n. Either way, Fn of x is eventually 0. Okay. All right, so that means this integral here obviously is not 1, it's 0. And obviously this limit here, this is just a constant sequence. It's true for every n. So this is 1. Okay. Yeah, not a whole hell of a lot to this. And you might be thinking, well, maybe what completely screws things up in general is just that this function essentially blows up as n goes to infinity, and that's not exactly what screws things up. Okay. So let's do another example. It's actually a little simpler. Not that the example I just did is hard, but so another example would be, let's say fn of x is going to be the characteristic function of n plus 1. And let's say here x is just in 0 to infinity. Or we could do even, not that it matters much, but let's do 1 to infinity. Doesn't matter, but anyway. Okay. So, right, what's the graph look like? Well, it's pretty obvious. Y, x, just a little bigger. So let's say we have n here, n plus 1. Let's say we have 1 here. So it's just a step function. Okay. And, right, so obviously this integral here, because we're integrating the step function, it's just like before, also 1. It's just the area under the step function. N plus 1 minus n is 1, times height 1 is 1. Well, anyway. So, right, this is another example. And I should also mention that, well, again, you can check very easily that on 1 to infinity, the limit function is going to be 0. And there's nothing subtle there. Pick any x between 1 to infinity. Pick n larger than x. Fn of x is 0. So obviously the limit point y is 0. Okay. Right, so this integral here, well, f of x is 0 almost everywhere on, 1 to infinity, not 0 to infinity. So the integral from last time is 0. And this, again, actually, let's call this e. Not that it matters all that much, but anyway. Right, so again, this limit here obviously is 1. It's a constant sequence. So this here, the integral of the limit, 0. The limit of the integral is 1. So you notice actually in both cases, the integral of the limit was less than or equal to the limit of the integral. And that's not coincidence. That's actually always going to be true when the limit of the integrals exist. Okay. And I should also mention that we know that if Fn is bounded and we're dealing with a set of finite measure, then we can always interchange limits and integrals if Fn converges to F. Sorry, if Fn is uniformly bounded. Okay. So in this case, the fn's are obviously uniformly bounded by 1, but we're not on a set of finite measure. E has infinite measure. So definitely here, the problem is that E has infinite measure. When E doesn't have infinite measure and the fn's are uniformly bounded, again, that's just a bounded convergence theorem that in that case, if fn converges to f, you can interchange limits and integrals. Okay. All right, so what we want to do first is, despite these examples, see what in general is true. And what is true in general is the observation we've made that the integral of the limit is less than or equal to the limit of the integral. Okay, and there should be a little L here, but right, so exactly what I said. If fn is measurable, non-negative, fn converges to f pointwise on E, then this integral is less than or equal to the lim-inf of these integrals. And that's even better than what I was saying, because we know the lim-inf equals the limit when the limit exists, the limit of these integrals. Okay? In general, it need not exist. So in general, we're replacing the limit by the lim-inf. And remember, the lim-inf always exists because it's the limit of a decreasing sequence of numbers. It could be infinity. I mean, in fact, each one of these could be infinity. I mean, you could have something silly like fn equals infinity on all the real line. And all this is saying is you integrate infinity over the real line. By definition, you can check to get infinity. So it's just saying infinity is less than or equal to infinity. The lim-inf of all these integrals, if each fn is infinity, is infinity. And the limit function, of course, is infinity on all the real line in that case. Okay. But still, infinity is bigger or equal to infinity, is bigger or equal to infinity, et cetera, et cetera. So in that sense, your first number is bigger or equal to the second number, bigger or equal to the third number, et cetera, et cetera. So the lim-inf always exists because we're taking the limit of a decreasing sequence of numbers, and that number might be infinite. All right, so what's the proof? Well, proof strategy is the same one that we've been doing all throughout the previous video. Let's pick an H less than or equal to F, non-negative, bounded, has finite support, and is measurable. And it's enough to show that this integral is less than or equal to the lim-inf. Why? Well, if the lim-inf is infinite, then there's really nothing to prove, because if this lim-inf is infinity, well, then this is trivially true. Infinity is less than or equal to infinity. Okay? So if the lim-inf is not infinity, then this real number is an upper bound for all of these integrals, since h is arbitrary. The integral of f of x over e, by definition, is the supremum of all these integrals over all these h's. So in particular, the integral is less than or equal to this upper bound, because the supremum is the least upper bound, and the integral is the supremum. Okay? So this is our task to prove. For an arbitrary h less than or equal to f on E, h bounded, measurable, finite support on E. Okay. So what we're going to do is cook up Hn in such a way to actually invoke the bounded convergence theorem, which is a reasonable strategy because that's all we know in terms of interchanging limits and integrals. Okay. Or at least that's the best we know. Okay, so first, let's just notice that, well, sorry, let's not notice anything. Let's pick a bound for h. H is bounded, so let's say h of x is less than or equal to m on E. And let's say E0 is a set where h of x is positive, same thing as a set where h of x is not 0 because h is non-negative. H has finite support, so the measure of E0 is less than infinity. Okay. So let's say Hn of x is the minimum of h of x and Fn of x. First of all, this is bigger or equal to 0, it's non-negative, because h of x is non-negative and fn of x is non-negative. Clearly, hn is bounded by m because h of x is bounded by m, and hn is the minimum of h and fn. Okay, obviously, hn is 0 away from e0 because, well, again, hn is the minimum of these, and if h is 0, hn is 0, and h is 0 on e take away e0. Okay. So what's a little less trivial, but still not very hard, is that I claim that the HNs converge pointwise to H on E. How do we prove that? Well, first of all, HN is less than or equal to H on E. That's trivial, because it's the minimum of H and Fn of x. All right, on the other hand, let's use the pointwise convergence of Fn to F. Okay, so let's say epsilon is bigger than 0. Pick n where f of x minus fn of x is less than epsilon if little n is bigger than big N. I mean, we can, of course, pick big N where the absolute value is less than epsilon, but we don't even need that. So what does this tell me? This tells me that I bring fn to the right-hand side of this inequality. I bring epsilon to the left-hand side of this inequality. So fn of x is bigger than f of x minus epsilon, as long as n is bigger than n. But remember, h of x is less than or equal to f of x on e. That's how we picked h. H is one of these functions. So h is less than or equal to f on e. So as long as n is bigger, little n is bigger than big N, fn of x is bigger than h of x minus epsilon. Okay, so what does that tell us as long as little n is bigger than big N? Well, hn is the minimum of these two. Again, that's the definition of hn, that's how we're defining it. Obviously, h of x is bigger or equal to h of x minus epsilon. That's trivial, because epsilon's positive. On the other hand, fn of x is bigger or equal to h of x minus epsilon for n bigger than big N. So both of these for little n bigger than big N are bigger or equal to h minus epsilon, so the minimum has to be bigger or equal to h of x minus epsilon. All right, let's put all this together. So this says that h of x minus hn of x is bigger or equal to 0. This here says that h of x minus hn of x is less than or equal to epsilon. So this obviously means the absolute value of h of x minus hn of x is less than or equal to epsilon if little n is bigger than big N. So yeah, that proves pointwise convergence. So now we can invoke the bounded convergence theorem. Okay. So first of all, we can't quite use bounded convergence theorem on E because E might have infinite measure, and as we've seen in this example here, well, bounded convergence theorem miserably fails in general if E has infinite measure. Nothing subtle is not exactly a terribly subtle sequence of functions here. Okay, but hn of x, again, by the way it's defined, is 0 away from, it's 0 on e take away e0, so we can excise that set. So each of these integrals is equal to each of these integrals over e0. Again, that's because hn of x is 0 on e take away e0. Now hn of x is bounded on e0. It's uniformly bounded by big M on e, so on e0, it converges to h on e, converges to h on e0, And E0 is finite measure, so bounded convergence theorem says we can bring the limit inside. But again, h of x is 0 on E take away E0. So this is the same thing as the integral of h on E. Now we can finally use the fact that, by definition of hk of x is less than or equal to, well, obviously, each one of these individually, so hk of x is less than or equal to fk of x on E. So by monotonicity, the integral of hk is less than or equal to the integral of fk. And you can combine this here with this fact to prove the result. And I assure you, this is just the definition of lim-inf, nothing more. And this is homework, so there's a lot of homework floating around there that I haven't assigned, and I will do that today or tomorrow, now that the exam is over with. So you can focus on not studying previous problems and doing homework. Okay, so I don't recall if I mentioned this, but the book calls this Fatou's lemma, and this is, no one else calls this Fatou's lemma. Fatou's lemma is similar, but slightly more general. And it follows almost immediately from this. So let's prove what everyone else calls Fatou's lemma. And I should mention this is extremely important, for example, in probability theory. If you Google Fatou's lemma for probability, you'll probably find dozens of PDFs that prove that state and prove Fatou's lemma purely using probabilistic language, because it's just that important. And yeah, if you go to Wikipedia, Fatou's lemma, there is a version in probability language, and there's even a version for conditional expectations, which is fairly deep probability, so I don't want to really get into that, but or even mention what that is, but anyway. Okay, right, so Fatou's lemma says if Fn are a measurable non-negative, then the integral of the lim-inf is less than or equal to the lim-inf of the integral. Now let me put this into context. The way you should think about this is basically all that can be said if you simply have a sequence of non-negative measurable functions. We have no idea if pointwise Fn converges to anything at all. Okay? So in absolute utmost generality, if the Fn's are non-negative, measurable, we can still say something, and this is that something. And this is still pretty powerful. I mean, in a lot of applications, you have a bound for all these integrals, and you want to bound this integral right here. I mean, I will admit, most often in applications, you actually use this here. And this is less general than Fatou's lemma because, of course, if Fn converges to F pointwise, then lim-inf Fn, as n goes to infinity, is F. Okay? So yeah, like I said, in practice, you often, most of the time, actually use this. And as I said, this is quite even useful because you often don't even know if this converges. You don't care. You get a bound for all these integrals that bounds the integral of f if the fn's converge pointwise. If not, the integral of the lim-inf. And I should mention again that because these are non-negative, the lim-inf exists. It's measurable. That was homework. So the integral of the lim-inf is perfectly well defined. And this integral, sorry, this limit of numbers exists, could be infinity. This could be infinity. Everything is well defined because lim-inf of non-negative numbers is a decreasing sequence of non-negative numbers, and hence converges, possibly to infinity, but it converges. And the proof is very easy. And it's basically the obvious thing if you're familiar with lim-imps. Let's say big Fn of x is the infimum of fk of x over all k bigger or equal to n. By definition of lim-imp, lim-imp Fn of x, which we're calling big F of x, is the pointwise limit of the Fn's. Again, that's not a theorem, that is the definition of lim-imp, period. So by definition, these Fn's converge to lim-imp Fn, little fn, and we call that big F. Okay? So from what we just proved, this lemma that the book calls Fatou's lemma, even though everyone else calls Fatou's lemma this one here, this integral here is going to be less than or equal to, pull out the lim-imp. Okay, well, trivially big Fn of x, should be a dx here, but whatever. Yeah, so it's kind of annoying me, so I'm going to put the dx here. Give me 1 second. Don't know why it annoys me, but anyway. Okay, so I'm happy now. All right, so big F of n is the infimum of all these fk's. Well, n is bigger or equal to n. So Fn of x is part of the set Fn of x, Fn plus 1 of x, Fn plus 2 of x, etc., etc. So Fn of x is bigger or equal to the infimum of all these fk's. Okay? Or in other words, the infimum is a lower bound for all these fk's. K equals n is in this set. So trivially, because we're dealing with an infimum, big Fn is less than or equal to little fn. So yeah, that's Fatou's lemma. Okay, and besides being, as I mentioned, extremely useful, and I've used it in my own research in this exact way, that you know, I want to get a bound on this integral here, and I can do that if I know some upper bound for these integrals here, even if I have no idea what the lim-imp is. But besides being extremely useful for that reason, it's very useful in proving something which is called the monotone convergence theorem, which I'll explain in a second. So let's just see what happens in a very special case that the Fn's are increasing. Okay, so let's say F1 is less than or equal to F2, is less than or equal to F3 on E, and everything's non-negative, of course. Okay, so the pointwise limit on E exists. It could be infinite. That's fine, but it still exists as a function from E, as a measurable function from E to 0 to infinity, including possibly infinity. Okay. Yeah, so this here is a little hard to read, but this is an integral sign. Don't know why it's so hard to read, but anyway. Sorry about that. Okay, so what does Fatou's lemma tell us? Well, sorry, let's not use Fatou's lemma just yet. So lim-imp of these integrals, again, by definition, is the limit of these infimums. Okay, but what is the infimum, of course, of all these integrals? Well, sorry, there's two integrals, so this integral should have been erased. The eraser didn't do a good job, but anyway. So pretend this faded integral is not there. Sorry about that. So, right, so what is the infimum? Forget about this limit here. What's the infimum of all these integrals? Well, the functions are increasing, So this is an increasing sequence as k goes from n to n plus 1 to n plus 2. So the infimum is obviously the first one, just the integral of fn of x. Okay? So again, this is forgetting about a limit. So the lim inf is going to be this limit here. Okay? So what does Fatou's lemma say? It says that this integral of f of x dx is less than or equal to this limit here. And I'm going to prove in a moment, in fact, and it's pretty obvious how to prove it, basically trivial, with this inequality, but in fact, equality is true. This integral here is equal, so the integral of the limit equals the limit of the integral, assuming the functions are increasing. Okay. So in this example, of course, these functions are not necessarily increasing. And in the example I had before, n times a characteristic function of the half-open interval 0 to n, that's definitely not increasing. So none of these examples fall under this scenario where the functions are increasing. It better not be, otherwise, what I'm saying is false. And also I want to make clear that things are not so nice. Well, sorry, I'll get to decreasing sequences in a second, but right. So we immediately, from what we've observed here, have what's called the monotone convergence theorem. So if we have an increasing sequence of measurable functions on E, these are all non-negative. So to make that absolutely clear, I'll write that in. So 0 less than or equal to f1 of x, et cetera, or f1, f2, et cetera. And if m is this pointwise limit, which again exists because it's an increasing sequence, could be infinity, that's okay, then we can interchange the limits and the integrals. And again, this is trivial from what we've already proved. So we've observed that this is true. So to prove equality, we just have to prove the opposite inequality. So it's enough to prove that this limit is less than or equal to this integral. Okay. Well, there's nothing to prove. Fn of x is less than or equal to f because Fn is increasing and f is the pointwise limit of, these increasing numbers, possibly infinity. So in that case, well, each one of these integrals is less than or equal to the integral of f of x. So then the limit, which exists because this is a sequence of increasing numbers, could be infinite. And again, if let's say all of these are infinite, well, it's increasing, so if one of these is infinite, then all of them are infinite. But if one of them is infinite, we're still considering that as an increasing sequence because infinity is less than or equal to infinity is less than or equal to infinity, et cetera, et cetera. So anyway, so this is trivially true. So this is true. This is true. So they're equal. All right, on the other hand, before I mention decreasing sequences, let's do an extremely important application of this. And that's to interchanging sums and integrals in the infinite sum case. So a very important consequence, almost immediate consequence, is if I have a sequence of measurable functions, then the integral of the sum exists. It could be infinity, but the sum absolutely exists because we're taking the infinite sum of non-negative numbers, and that always exists. Right? So let's write this as the limit of the partial sums. Well, the partial sums are obviously they're obviously increasing. So actually, not to have a little detour, but if you're wondering why I have this Hershey mug, my girlfriend is a first-year resident in Hershey, so a little sweetener here. But anyway, right. So we can use the monotone convergence theorem here because partial sums are increasing. So we can pull out this limit, but we know, and we've proven that for finite sums, we actually did it for sum of two functions, but easy induction proves it for the finite sum of any number of functions. Finite sum. So, right, so we know that the integral of this finite sum is the sum of this finite integral, but these are non-negative numbers, so the finite sum as n goes to infinity exists, and that's the infinite sum. So we've carefully proven that the integral of an infinite sum is the infinite sum of an integral as long as we have non-negative measurable functions. Right, and as an easy example where the monotone convergence theorem can miserably fail for decreasing sequences of functions, let's just look at a very easy example. Fn of x is a constant function, 1 over n on the real line. Well, the limit function is just 0. So the integral of f of x dx is 0, but obviously the integral of 1 over n on all of r is, well, infinity. So, I mean, the picture is fairly obvious. Sorry about that. So here's 1 over n. It up a tiny bit. Right, so this is just this constant. Anyway. Right, so yeah, so trivially the integral of this constant 1 over n on all the real line is infinity. So all right. So 0 is not equal to infinity, though still this again illustrates Fatou's lemma that the integral of the limit is less than or equal to the limit of the integral. That's true in dramatic fashion. 0 is less than or equal to infinity.